My name is Sina. I'll be presenting locally adaptive cellular automata for goal-oriented self-organization. Let me turn this thing off for a second for myself. Okay. So in this talk, I'm going to present a set of methods, pretty general set of methods to implement parameter localization in cellular automata that's still fast and allows for interactive development and experimentation, which was one of my primary goals to work on this project. And then I'm going to show a few examples, some implementations of this method with two models that are of interest to me, which is self-organizing to criticality Ising models and a plastic leaky integrating fire neural network. And to begin, I want to start with a quote by von Neumann. So he says in one of his lectures in the late 40s on computing machines, quote, "I want to point out that there are large areas in pure mathematics where we are blocked by a peculiar interrelation of rigor and intuitive insight, each of which is needed for the other, and where the unmathematical process of experimentation with physical problems has produced almost the only progress which has been made." So von Neumann here was talking in the context of turbulence and sort of the gap between linear and nonlinear systems, and a lot of the progress in physics and these kind of mathematical systems in that, and still to this day, were always done in conjunction with experiments. Solving these nonlinear systems is quite hard, but we can make them, and that's why so much of physics relies on these kind of experimentation. And we sorely miss that in complex systems, and so there's a motivation here to build complex systems, and I guess a lot of us here in ALIFE are exactly motivated by that, and to see how complex systems actually look like when you can look at them from a bird's eye view or like a godlike view. So for me, I studied physics originally, but when I joined my group in Tübingen that does computational neuroscience, I didn't really have a strong intuition for like what a million plastic spiking neurons might look like. And furthermore, when you actually implement any of these models, they have so many parameters and hyperparameters that actually tuning them to a sort of quote unquote interesting state is kind of difficult. You have to either know what you're doing or just play with the parameters long enough until it does what you want it to do. And so, yeah, there was this question is if there's a way to introduce feedback mechanisms to tune or control systems into these interesting regimes. I just have a phase diagram of this reaction diffusion system here where you can see changing the parameters leads to different types of behaviors. And usually it's the case that there's a particular spot in the phase diagram where we care about. So to begin with, I know a lot of people have already been talking about CA, so I won't go into too much detail. But in general, they're discrete models. Usually you have a grid of cells with a finite number of states, one or two states, sorry, at least. And each cell has a neighborhood, and the update rule is usually a function of the center cell and its neighborhood. The nice thing about CAs is that they're very parallelizable, and usually that depends on the fact that every cell is updated according to the same rule, which is a pretty annoying constraint when you want to model something slightly more heterogeneous or natural. And so yeah, that was the question that kind of started this project: is how can we model heterogeneous systems where the update rules are a function of its history and its context. So I introduced a set of methods, or rather a method, to introduce heterogeneity in CA update rules. And so this allows us to introduce like adaptation, local adaptation, and you can do all kinds of different things with it. But in my case, I want to show off a self-organizing to criticality model, and also we implement this with some synaptic plasticity in a spiking network, just to see if it can do it. So the basic idea is that if a classical CA is a function of the neighborhood and whatever parameters which were fixed at the beginning, an adaptive CA has these parameters, or it's essentially like a coupled CA. You have the parameters are embedded within the state of the system, and they themselves can evolve. So you just have two coupled systems here. The trick to doing this is rather simple, and it comes from the sort of the progress of computer hardware and software when it comes to doing linear algebra really, really fast. And from the machine learning world, there's a function called image to column, but it's also known as unfolding or patching, where you basically take a matrix like the one over here, and you take little patches of it and you unfold them and vectorize them in this way. Doing this, you can basically do any kind of sliding window operation. So if you're doing a convolution, under the hood, what's happening is basically you're unfolding this. You then, I'll go to the next slide, which I explain a little bit better. You take a patch and you dot multiply it by whatever kernel you have, this element-wise multiplication, and then you sum it. And if you do this for every patch, that's what a convolution is basically doing under the hood. There's more optimized algorithms that do like Fourier transform versions of this, but this is basically what it's doing. And what you can do is you can basically replace the operations in this loop with whatever you want. And the sliding window operation doesn't just have to be a convolution. In fact, you don't even need to sum it at the end. You can keep it in matrix form, and you can have like a very high dimensional object. A very high dimensional object. So here's I'll quickly show off our spiking neural network implementation of this. So on the left is first, this is the leaky integrated fire model. Basically, the voltages are a function of if there are spikes in your nearest neighbor or just your neighborhood, whatever that neighborhood is. And what we find is that we can create asynchronous irregular statistics. It's not super important what that means, but the idea is that we can kind of replicate the statistics that we observe empirically in the brain. And I was quite happy when I made this simulation, and this is kind of a small version. It's 360 by 360, but it ran on my laptop live, 60 FPS, 100 FPS, and I can scale up to 1 million neurons. And so the scalability of this was impressive. As far as I knew, I couldn't find any projects out there that had these kind of interactive models at this scale. So I also combined this with Pygame to be able to play with this, and I can't show it off now, but you can click and you can turn features on and off, and it was just the nicest way for me to build an intuition about how these models work. And I think that's what I was severely lacking coming into the complex system world, is this intuition of, okay, if I change this feedback rule, or if I change the connectivity in some way, what actually happens in the system? Like, can I start to build intuition from the bird's eye view? Because we have intuition of complex systems from the subjective level, because we're all embedded in it. But from a bird's eye view, it's a little bit more complicated. But after making this, I wanted to, well, actually, there is one more thing about this. So we introduced plasticity in this model. And here I have an image of Ginger the pug. Ginger the pug, yeah, that's what I said. And we have two rules for excitatory and inhibitory neurons, which we have both of in this population. It's not, again, super important for this presentation what these rules are, but the inhibitory rule is trying to achieve homeostasis, and the excitatory rule is doing some kind of Hebbian learning. And what we find is that we can essentially drive the system with this image, and the connectivity pattern that emerges is kind of reflecting this. And so this was a proof of concept at the beginning that, okay, we can do spiking neural networks really fast. We can then drive them and have this plasticity rule implemented, and this all happens relatively quickly on the GPU. But after this, I wanted to move on to something that is a little bit more well-studied and also more familiar to me coming from physics, which is the Ising model. So the Ising model is the sort of quintessential or foundation model for phase transitions and the observation of critical points. Really quickly, I'll summarize what the Ising model is. It's sort of like a stochastic CA. I mean, it basically is a stochastic CA. You have cells or spin sites that can be either in a +1 or a -1 state, and they're connected to their neighbors according to some connectivity Jij. And they're trying to minimize their energy. And you can simulate the behavior of this model without actually solving it analytically with a like a Metropolis algorithm, or there's a couple different algorithms that can do it. But in general, the probability that a spin will flip to a different state is a function of the connectivity to its neighbors and the temperature. Basically, if the temperature is really high, it's constantly flipping between two states. And if the connectivity is really strong, then it's trying to align itself with whatever its neighbors are. The connectivity can also be negative, and then it'll try to anti-align itself, but then it'll kind of be frozen in a state. So the Ising model has a known critical temperature and a lot of, it's again, very well studied about how it behaves near its phase transition. And we wanted to see if we could bring this model to its critical point just by running it. So usually you have to tune systems to their critical points. It's really not trivial. Some systems don't have critical points. And it would be kind of nice if there was some type of adaptation rule or some kind of mechanism that can bring a system to these quote unquote interesting states. So the first implementation that we introduced was adaptive temperature. I introduced local temperatures at every pixel or spin site. And we came up with this equation here. And it's not super important what this equation is. We handcrafted it. I'm sure there are other versions that also more or less work. But the general premise is that the temperature is always trying to decay. There's a diffusion term, which is just spreading this information. And there's a growth. The temperature increases if the model is too ordered. So M here is the magnetization of the system. So if everything is aligned in the same direction, the temperature tends to increase. And in the video on the right, what you can see is that originally the model starts in an ordered state. So there's like there's very big clusters. But as I run this algorithm for just a few frames, the temperature very quickly converges to the critical temperature. So it is a broad distribution, but from the avalanche dynamics or the avalanche statistics, it's pretty clear that it's in a critical state. So the known critical temperature for the Ising model is around 2.2691 for the 2D Ising model, and we see that our algorithm basically brings it to that point as well, at least the average. Now this is relatively easy because the temperature is a scalar, and I'm still not using the full extent of the capabilities of my method. So we tried to make it a bit harder by introducing adaptive connectivity. So now the temperature is fixed. We set it to 1, but the relationship to the neighbors can be constantly changing. And here we came up with another rule, and this one, the idea was that if your neighborhood is too ordered, then you should disconnect them. So this is trying to disconnect ordered pairs, and then this term here at the beginning is trying to connect disordered pairs. So if the system is too random, it'll try to pair neighbors together to kind of bring some order to the system. In the visualization on the right, I've overlaid both the connectivity and the spin dynamics on top of each other. I hope it's somewhat legible, but the idea is that once again, the system starts in a highly ordered state, and very quickly it relaxes to the critical temperature, and it doesn't overshoot it either too much. So it actually does stay there if I run it long enough. The next, and also when we measure the statistics for the connectivity, we find that it does once again converge to the critical connectivity, which if you set the temperature to 1, then you can kind of calculate what the critical connectivity ought to be, which is around 0.44, and we do get something close to that. So once again, it seems to more or less work. And this is again with just handcrafted equations that we just trial and error for like a day. Then there was one more level of complexity that we wanted to add, and this is slowly trying to get into the world of like the real heterogeneity in the world, where there's constraints and there's some areas that they're basically just constrained by different mechanisms. So here what we do is we introduce this concept of like zealots, where a percentage of the pixels are fixed in either a +1 or a -1 state. So in the video on the right, you can see like these areas where the blue just is fixed. These are the spins that are frozen. So this is going to push the system. It's going to bias the system heavily into an ordered state. And to bring this system to a critical point is much more difficult once again. And so we use the exact same adaptivity rule as before, and it does converge once again to a critical point. And we guarantee that it's critical by measuring some of the thermodynamic variables or observables of this. So in the Ising model, the traditional ones are the energy and the magnetization, which then are paired with the specific heat and the susceptibility. And so these are usually, these are the variances of energy and the variances of magnetization. And in thermodynamics, when these properties diverge, it's usually indicative of a phase transition or a critical point. I say usually because there are sometimes sometimes it's not, but in any case, in this case, we seem to find that our model, even in the context of the zealots and this highly biased system, is still able to bring it to a critical point. So that's pretty much the project so far, but we have a lot of ambitions for this project because we haven't tried to actually optimize anything here. So far, this has been handcrafted adaptivity equations or models that are already well studied, like spiking neural networks that are plastic with known plasticity rules. But there are a lot of things in the context of ALIFE that are quite curious for me, which is, for example, stuff like maximizing entropy production or extracting work from a system or from a heat source, creating boundary conditions where there might be things like engines, or try to see if we can evolve an engine out of the connectivity pattern of this like Ising model. And from the world of neuroscience, the idea of balance in driven systems. So even when you're perturbed, to bring it back to a state of balance, and also to distribute information. So we have some ambitions there to, in the near future, to run these things through some evolutionary algorithms and see if we can induce some complexity and structure in these kind of physical systems, or not physical exactly, but abstractions or models of physical systems. Yes, so yeah, in conclusion, we introduced the method to have heterogeneous and adaptive update rules in CAs that are still fast and interactive, so we don't lose any of the benefits of CAs by having this heterogeneity. We lose some, but not enough to actually destroy it. And then, and I showed you the self-organizing to criticality stuff, which I think was quite neat. And yeah, that's it. So thank you, and thank you to my group for helping me with this project. If you have any questions, please let me know.